Alrighty, so now we're going to talk about net force equations. And all a net force equation is taking what forces you have in your force diagram and putting them together in terms of what the forces are in the x direction and what they are in the y direction. All right, so the way that we're going to think about this is add them all up in one direction. And I like using to the right is positive and to the left is negative, just like in math class. And that's for the x direction. And then for the y direction, I like making it so up is positive and down is negative. So I can add all of my forces together, and I have, if it's going up, it's going to be a positive number. And then if it's going down, I'm going to subtract it. So all of your forces are always going to be positive numbers. And then if I make it a add or a subtract, then that's going to be with regards to if it's going to the right or left versus up or down. So this is the big ta-da, equation F equals ma that you are probably familiar with already. Unfortunately, this does not just tell you, okay, whatever that one force is, it's going to equal its mass times acceleration. What this really is your net force. And what that means is if you had 10 newtons of force going to the right and 4 newtons going to the left, then your net force would be the 10 minus 4, which would give you 6. So the units for force are newtons, which is a capital N. All right. Okay, so we're going to start with this equation, the F equals ma. And I'm going to have an object in free fall, which is exactly what we were doing when we were doing projectile motion. So there's only one force acting on my object, and that is the gravitational force. There's nothing slowing it down. There's nothing pushing it right or left. And so using this F equals ma, the only force acting on it is my gravitational force. And then I'm going to have equals ma. Well, we know from last time that Fg, or our gravitational force, is equal to mass times my gravitational field strength. So I'm going to substitute in for my Fg with mg. All right, so now I have mg here on the left, and I'm just going to transfer the ma right down, so that does not change. Then you'll notice that on both the left and the right, I have mass. So I'm going to divide both sides by mass. And the masses will cancel out. And I'm left with G is equal to A. That means that the gravitational field strength, which on Earth is 9.81 meters per second squared, is going to be equal to my acceleration, 9.8 meters per second squared. And that's exactly how we get the acceleration for an object in free fall. And that's also why it doesn't matter how much an object weighs. That's going to determine how fast it falls, or the acceleration in which it falls. Now, unfortunately, that's not always the case. We know that sometimes there is air resistance. So for example, if I have an object here that's falling, let's say a dude with a parachute. Okay, that's my beautiful guy with a parachute. And so he has gravitational force acting on him, but he also has some resistance holding him back. And let's say he just put out a parachute and it's too small, so he's going to still accelerate towards the ground. Then I could have a small force up, and we could call this a tension force, because it's the ropes that are really pulling on the actual guy. So we'll define our system as the actual guy that's falling. All right, so, and then this part here, so this is the required part, the FT and the FG. And as you get better at this, I will not require you to write out all of the stuff, but this would be on Skydiver by the Earth and on the Skydiver by, we'll call it the ropes. Okay, so where these net force equations come in is that I need to account not only for the forces that are acting on him, but all the forces that are acting on him. So I'm going to add up all of the forces. So that's what this symbol means. This is the sum of the forces in the y direction. And so I'm going to recall that I want up to be positive and down to be negative. All right, so in this case then I have tension pulling him up. So I'm just going to write the FT. I'm not going to write the other stuff. And then minus what goes down, which is FG. And that'll be equal to my mass times acceleration. Now the acceleration of this guy is not going to be 9.81 because the only force being applied to him is not just gravitational force. He also has a tension force being applied. So now what you would do is you would be given numbers. So let's say the tension here is 20 and the gravitational force of this guy is 60 newtons. And let's say his mass then, we could figure out what his mass is actually, because we know that gravitational force is equal to mass times g. Well, if his gravitational force is 60 and mass, and then g on Earth is 9.8. So I just need to divide both sides by 9.8. And I get 6.12. So 6.12 is my mass. So that's going to be 6.12 kilograms. And I had this tension as 20, gravitational force as 60. So all I need to do then is plug stuff in. So 20 minus 60 is equal to my mass, which is 6.12 times my acceleration. So this would be, I'm solving for his acceleration. So this would be negative 40. Divide both sides by the 6.12. Now I get an answer of 6.53 meters per second squared is my acceleration. So you'll notice you don't only keep track of one force that causes acceleration. In reality, it's this sum of the forces. Now, the tricky thing that a lot of students have with this is that they don't realize that every single scenario is going to have a different net force equation. And this thing is called a net force equation. So you need to learn how to do it and not just memorize what the net force equations are. All right, so here's another example. We have a boy is pulling a wagon, so it accelerates to the right, and there is friction. If the boy pulls with 5 newtons and the friction is 2, and the mass of the wagon, cat, and dog is 15 kilograms, then we can create a net force equation for this boy, or for the wagon, I mean, for the wagon, and solve for my acceleration the same way that we did for the skydiver. So the force from the boy. So the first thing I want you all to do every time is draw a force diagram for this wagon. So we have normal force and gravitational force. And we have a tension from the boy. So this is Ft. And then our friction is Ff. And it's smaller. And then I'm going to make sure that my normal and gravitational forces are the same. So then all you need to do is plug in the numbers and solve. So the 5 newtons from the boy pulling goes there. The 2 newtons of friction goes here. Notice it's a subtraction because one goes to the right and the other goes to the left. And then your mass goes in for the mass. So we've got, when you write the equations, what goes to the right minus what goes to the left. And when we're going up and down, we have the forces going up minus the forces going down. When acceleration is 0, then this acceleration, it becomes 0, which means then this is when you have a constant horizontal velocity or a constant vertical velocity. So it still equals ma, but when the acceleration is 0, mass times 0 will equal 0.